before that, I'll just ask you, sir, one or two questions. If I share the questions, I think you have no problem
No,
regarding your.
I do not have
Actually,
any
sir. No, actually, sir. I think you have assigned to solve some specific problems. Okay.
Yes, I cannot solve the assignment problems now because I
Okay.
haven't seen the
Okay.
assignment and I am not prepared for that particular. I don't know which topic is
So
that.
you just
Okay.
whatever, sir. But you
I
just giving some idea.
Yeah, I can give you. I can give you hints. I can give you.
Okay, sir.
Definitely.
No, I just want to know that it is not any problem for you too.
Uh,
But
I won't solve the questions. I will just hint you. Okay, there is no problem.
no. Actually, sir, I just want to know that if I share question, you have no issue though.
No, I do not have an issue.
Okay. Okay, sir, I shall share the question. Okay.
Okay, sure.
Sir, is the my screen is visible, sir?
Let me see. Just give me a minute. No. Just give me 1 minute. Just give me one. Yeah, your screen is visible.
Sir, you you can see the question, sir.
Let me see. Can you just zoom in? Okay. Can you just read out the question? I'll see.
Yes, sir. No issue. A bias is provided to a MOS capacitor such that
Hmm?
the minority carrier is semiconductor accumulates near the oxide semiconductor interface. The MOS capacitor is operating in which of the following region?
Okay. What I can get it, there are some more questions, right? Uh,
Yes, sir.
okay. I will show you some. I will give you some basics about the MOS capacitor. Okay. That will be
Okay, sir. Okay, no issue.
okay. I'll just check if I have the. I have the presentation for that MOS. Just give me 1 minute. Okay. Just
Okay, sir. I can stop the sharing. Okay.
yeah. Yes. You can uh, uh, turn off your screen. So I'll just see. I just
Okay,
need
sir.
some time.
Okay, sir. No issue.
Just give me 2 minutes. I'll just see.
Okay, sir. Okay, sir.
Okay. Just give me 1 minute. Uh, Can you see my screen?
Yes, sir. Yes, sir.
Okay, I'll just try to tell you about the MOS because I'm not prepared for that. This is a long back. I prepared slides for this.
Sir, no issue, sir.
Okay, but I will just
Actually,
try
sir,
to. Uh,
whatever you sir share, that will be helpful for us, sir.
okay.
Nothing else.
Yeah, sure. So, okay, this is fundamentals of semiconductor devices, tutorial 7. So, I'll be discussing about the most CV characteristic, most cap about most cap. So, speed type substrate. Because I'm not prepared for that. I also need to look into at the same time. Okay, okay, so this is given the most CV. So for the low frequency region and the high frequency region, do you understand about the most CV characteristics? So how they come and do you know anything about the most? Okay, okay, I'll give you one thing. You will understand a bit more. Okay, so just understand this thing. This is your hmm, there is a substrate. Okay, and this is a semiconductor. This is a oxide layer, which is dielectric layer, and there is metal over that. Metal, oxide, and semiconductor. This is the MOS. Okay, so whenever you apply some bias over this, let us say the positive voltage, and this is grounded. Okay, let us say you apply some positive voltage at the metal on the top. That is, you can say the gate or something. When you have a MOSFET, that is the gate. Okay, so this is the MOS device: metal, oxide, and semiconductor. Do you understand this thing? Okay, I hope that you understand this thing. And
Yes, yes, sir.
okay,
Yes.
let us say this is N-type semiconductor. N-type. Let us suppose this is an N-type semiconductor. When you apply a positive bias here, positive bias at the metal, so there will be accumulation of the electrons at this junction. Okay, this is electron, electron, electron. This is the accumulation in near the uh, this oxide semiconductor at this interface. Okay, so because you are applying a positive voltage, so there will be an electric field that will be in this direction from positive to in this direction. So there will be an accumulation because this is N type. So when you apply a negative bias at this junction at this metal, so there will be an so these electrons will move away from the from near to the junction. This is N type, so the electrons will move away. Okay, because we are applying a negative, so this electric field direction will be in this direction. Okay, electric field will be in the upside direction, so electrons will move away. So there will be a depletion region. Initially, there will be a depletion region. Okay, initially there will be depletion region, but when you increase the voltage in the negative direction, okay, when you increase the voltage in the negative direction, there will be a point that it will come. So it so it will knock out the holes here. There will be a inversion layer will holes will appear here near to the this depletion region, near to the interface. Okay, that is the initially it was accumulation. When we are applying a positive accumulation, then comes the depletion region. When you go in the negative direction, depletion region, and when you go more and more negative, uh, you apply more and more negative potential at this junction. So there will come uh, the there will come the inversion layer. Okay, inversion.
But sir, hello.
Yes.
Sir, actually, sir,
Mhm.
the maximum negative voltage that we
Okay.
apply
Mhm.
uh, in the N side.
Mhm.
sir, what is the maximum voltage I can apply to an inside?
You can apply as much as you can, but that the band bending won't go beyond certain limit because there are interface charges. Okay, because of that, it won't go beyond. So maybe I can cover that thing. There is something trap charges or Fermi level pinning. Okay, because of that, it
Trap.
won't go beyond.
Okay, sir. Okay.
Today I won't cover
So,
that
sir,
thing.
the maximum,
Mhm.
okay, maximum reverse voltage that we applied in the N-type region, inversion occur. Okay.
Yes. Okay. So
The
okay,
maximum
I will
amount of
show you.
reverse.
Mhm. Okay. I will show you in this one. You will get to know that thing. Okay. In this one, yeah, in this one. Okay. Should I go? I teach this thing or start this thing? Accumulation, inversion, and depletion. So, do you understand the band bending and these things in a semiconductor?
Sir, if you recap little bit, it will better, sir.
Okay. I'll
I
show
know
you.
that, sir.
Okay, I'll show you that. So this is the same diagram I made in the previous slide. Okay, this is a metal. This is an insulator, which is oxide, and this is a semiconductor. Okay, and this is one another contact we have taken here, which is grounded. Okay, understand and got this point. Okay.
Yes, sir. Yes, sir. Yes.
So if you see in a band diagram thing, so it will look like this. This is metal. This is oxide, which has a very wide band gap. Okay, because this is an insulator. Okay, and another one is this is N-type semiconductor.
Okay.
Okay, in this is N-type semiconductor, and the same thing is shown in for a P-type semiconductor as well here. Okay.
Yes, sir. But the difference is that in case of Fermi level will be in the valence band for P-type and Fermi level towards the conductor band in N-type. Okay.
This thing. Okay. So when we for a P type, this is for a P type and this for N type. I will tell you about for the P type. When you apply a negative potential for a P type, okay, so there will be an accumulation of charges near to the interface. This is the interface. Okay, in the semiconductor.
Okay, sir.
So there will be accumulation of the charges. Okay, let us say when you apply negative potential, negative will attract the holes, right?
Yes, sir.
Negative potential, if you do more and more negative, it is P type, it is abundance of holes. There are abundance of holes. So it will attract holes here. So that is the accumulation. Okay, that is accumulation. Can you see the holes here? Right?
Yes, sir. Yes, sir. Yes, sir.
So these are the holes here. So when you apply positive potential, V greater than 0, okay, so it will attract the electrons, but electrons are minority carriers in the P type.
Yes, sir. Yes, sir.
Okay, but if you increase the potential in the positive direction, it will attract more and more electrons here. Okay, it will generate electrons actually. If you apply more and more potential here, so there will be electrons. Can you see the electrons here? So this is the
Yes, sir. Yes, sir.
this is the inversion of the charges. Inversion means because as we took P-type semiconductor and we have created N-type carriers here, electrons here. So that is the inversion. Got the point?
Yes, sir. But sir, in case of depletion, the holes are way out and make some phase charge region. Yes or no?
Yes, definitely.
Okay, sir.
Okay, so if you apply more and more potential, so there was during okay, in this case, so there is some can you see this one, this gap between EF and EI?
Yes, sir.
So this defines this will
N-type.
yeah, this gap will give you the carrier concentration. Okay, N-type carrier concentration. Okay, so this gap, between EI and EF will give you a P type, a P carrier concentration, holes carrier concentration, right?
Yes, sir. Yes, sir.
Okay, if you remember the formula or if you can recall something, okay, it will give you, okay. So if you apply some such potential such that this gap, this Fermi level will go below the EF, okay, below the EF, the same amount, EI minus EF, okay. So the same. So this is the inversion of the charge carriers. Okay, we apply the potential of above that. That is the, we can say, the turn on voltage or the inversion voltage.
Sir, one more time, sir.
Okay, one more time. So can you see this gap, EI minus EF, this gap?
Yes, sir. Yes, sir. Yes, sir.
So when you apply the potential, can you see this gap at the interface is at this interface, this gap between EI
Reducing,
Mhm.
reducing, sir. Gap is reducing.
Gap is reducing now. So if you apply more and more positive potential, so this EI, this EF, this the band bending will be more and more, right?
Yes, sir. Yes, sir.
So this band bending will cross this EF, right?
Band bending is close to EF. Yes, sir.
Yeah, it will cross the EF then, right?
Yes, sir.
Okay. So do you understand when the band bending EI is equal to EF, what will happen at this point? P is equal to N. Number of charge carriers will be equal at this junction. Do you understand these
Okay, sir.
things? Okay, you need to go back in the second or second lecture. Okay, once just see so how the Fermi level and
Actually, sir, when EI equal to EF,
Mhm.
it means that it is intrinsic in
It
nature.
means, yeah, exactly. So P is equal to N
So,
at
sir,
that point.
N equal to Ni square.
We cannot say that thing. In equilibrium, that doesn't happen.
Okay, okay. In equilibrium.
Okay. So because this is the in equilibrium, not in equilibrium. Okay. Non-equilibrium conditions
Sir,
doesn't apply for that. Yes.
it is not equilibrium due to just that metal Fermi level and the semiconductor Fermi level different region, na?
No. It is not. It is non-equilibrium condition because we have applied the potential.
No, sir. Actually, sir, in equilibrium condition,
Mhm.
the Fermi level of metal and Fermi level of semiconductor are in a equal line.
Yes, that is equal because okay, at this point you can see, right?
Yes, sir. Yes, sir. Yes.
So that is because there is no current flowing.
And also, we are not applying voltage to the on the metal side.
Yes, but band bending can happen if the Fermi level difference is there. If the metal work function and this ionization energy, I think this is the ionization energy or what we call it. I forgot this thing. Or
This
I
is, sir,
think
chi function, chi.
chi function is there, but what do we call it? Ionization energy.
Affinity, electron affinity, sir. Electron affinity.
Electron affinity. If these two things are unequal, so then there will be some bending. Okay. So at that time,
Okay, sir.
so there will be some bending, but this Fermi level will match. There will be definitely bending because of the electric field. Okay. Inbuilt electric field.
Okay, sir.
Okay. So in this one, so you got this point. So inversion, when there is accumulation, depletion, and inversion happens. This is the depletion case. This is the accumulation case. This is the inversion case.
Sir, it means that I can just summarize that in case of inversion, we applied uh, less than zero negative voltage, and the holes are attracted near the
No,
valence line.
that is the accumulation
And-
for P type.
Yes, sir, accumulation. And
that
in
will-
case of inversion,
Hmm.
we have applied some positive voltage.
Mhm.
Due to that, holes are repelled back,
Mhm.
and there is a depletion capacity region is formed.
Yes. In this
And
one,
in case of your
inversion.
inversion,
Mhm.
actually we have applied more positive voltage
Yes.
so that
Mhm.
the minority carrier will be minority carrier will be accomplished near the junction.
Yes. 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 That is the
Okay,
inversion.
sir.
And in N type, the potential polarity will change. Okay, the polarity will
No issue,
change.
sir. No.
Okay, so you got this point, right?
Yes, sir.
Huh. So, anything else you want to? Is there any meeting? Yeah, you know. No, no, I heard no. Uh, the meeting will be a bit longer, so have you booked this meeting? Yes. Okay, sir. Doing something? Yeah, actually, NPTEL tutorial. NPTEL tutorial is coming. Oh. So, I'm so sorry, sir, have you booked? No, actually. Okay. Hello.
Yes, sir. Yes, sir.
Huh. Okay, these things I need to go a bit more. So, have you seen this thing somewhere? So,
Yes, sir. Yes, sir.
did you understand all these things?
Sir, not all this thing, but
You
I
can ask me.
learned the formula, sir.
Okay. I'll tell you. Okay, I'll tell. I need to go with the terminologies first. Accumulation of holes, flat bend, Fermi level at mid gap. Okay, I'll see. Okay, QM, the charge carriers. Okay, is the an inversion depletion. Okay, so the thing is in here, what it is saying is, so when you apply a potential, okay, this is in a strong inversion region. Okay, this is a p-type semiconductor. Okay, p-type semiconductor. When you apply potential at a metal, so what will happen is there will be accumulation of charges in the metal itself. Okay, do you understand that thing? Do you
Yes, sir.
understand?
Yes, sir.
Do you understand just take a two parallel plate capacitor. Okay, in parallel plate capacitor, when you apply a potential, so there will be, let us say V, you have applied a potential V. Okay, according to the capacitance of the capacitor, Q is equal to C into V,
Q equal to CV.
right?
Yes, sir.
Right. So
Yes,
in
sir.
metal, that let us say that QM charge is accumulated at the metal plate. Okay, in semiconductor there are two things. So in inversion, in strong inversion, there is the here in this region. This is the inversion region because there are electrons and the Fermi level is below the Fermi level is above the intrinsic Fermi level. Okay. So in this region there are holes. Holes are also there. Okay. So.
Sir,
Mhm.
sir, whatever you can tell, sir, as per Q equal to CV formula, if I applied voltage is there,
Mhm.
if I applied voltage is there,
Mhm.
so some charge accumulation is there in the metal band. Metal.
Yes.
So then your P-type semiconductor will be band bending is there.
Mhm.
Then, sir, whatever you tell, sir.
And because of the band bending, there is a depletion, there is inversion of the charges, right?
Yes, sir. Due to applied forward voltage, sir.
So, in the inversion region, which is greater than the when it makes the inversion. Got the point? Okay. Uh-huh. I couldn't hear you. Hello, Somnath.
Yes, sir. So there is a inversion region occur due to the applied forward voltage, which is much higher voltage.
Yes. Yes. Got the point? So because of that, there will be
Yes, sir.
electrons. There will be electrons at this interface, right? At this interface.
Yes, sir.
So that the electrons will be Qn. Okay.
Okay,
And
sir.
that will be very thin. That will be very thin. Okay. And
Okay, sir.
and another thing is because of the immobile charges at this point in this region, there will be some immobile charges, right? That is uh, because of the doping. Okay, that is the QNA. The
Okay, sir.
carrier and QNA into WD. What is the depletion? Whatever is the depletion region width, QNA into WD.
Okay, sir. Okay.
That
Sir,
that
why,
charge-
sir? Why, sir? Means deflection which is forms at UNA.
Okay, depletion region will definitely form because of the band bending, na? Because of we are applying the potential, so uh, it is depleting the charge carriers from here because we have applied a positive potential, so it is uh, throwing away the holes this side, right?
Okay. Okay, sir.
So
Okay.
it is
So
depleting
at
the
the
holes.
interface,
Mhm.
at the interface, there will be some electrons are accumulated,
Mhm.
but due to repulsion of holes,
Mhm.
there will be a region where we got some ions are there.
Ions will be immobile ions will be because of because immobile ions will always be there in the whole
Sir,
semiconductor. Mm-hmm.
one call is coming, sir.
Mm-hmm.
Can I take one call for 1 minute? For 1 minute.
Yeah, sure.
Sorry, sir. Sorry.
No problem, sir.
Sorry for. Okay, sir. Sir. So, as per your, due to the positive voltage applied on the metal side, the charge will be accumulated near the interface.
No, charges won't accumulate here. The charges, which charge are you asking? Because it is inverting the charge carriers because of the positive.
Electron.
Mhm. Okay.
Yes, sir. Electron are accumulated near the interface.
Yes.
Electron are accumulated near the interface.
Mm-hmm.
And sir, and holes are due to holes repulsion, the depletion region is formed.
Yes, we can say that.
Okay, sir.
Mhm. Okay, because of that, there will be this much of the charges in the semiconductor side. Got this thing?
Yes, sir. Sir,
Okay,
this is a total charge, no?
this is the total charge. And,
QN for,
due to
QN for
inversion
the.
and due to depletion.
Okay, sir. Okay.
Mhm.
Sir,
Okay,
QN for the electron charge and QNAWD is the depletion region charge.
yes, yes.
And the minus QH will be the surface charges.
No, this is the total charge in the semiconductor.
Or total charge in semiconductor. And this is a total charge in metal.
This is total charge in metal.
Okay, sir. Okay.
Okay. And the thing is, V is equal to the potential that we have applied will drop in the insulator region. Okay. And
Yes,
there
sir.
will be in semiconductor region. Okay.
Okay, sir.
And the semiconductor region drop charge will be equal to the band bending. That okay, the built-in potential that you have studied in the PN junction.
Okay, sir.
Okay, so that this band bending is because of the application of the voltage, right?
Okay, sir.
Yeah, and this is this much voltage is dropped across the insulator.
Okay, sir.
Okay, so that is equal to the potential that we have applied V. Got the point?
Okay, sir.
Okay, so
Sir,
yes.
sir, whatever you tell that above the insulator,
Mhm.
the top point of the insulator to the starting point of the bottom part of the insulator,
Mhm.
this is the voltage drop across the insulator.
Okay, so
And psi s is the due to band bending semiconductor voltage, right?
okay, one more thing. Okay, let me tell you one thing. So, what is the V is the applied voltage. Okay, whatever the voltage that we have applied across this device, let us say this is the device, whatever the voltage that we have applied, this is this. This is the MOS. Okay, got the
Okay, sir.
point. So, in MOS,
Yes, sir.
how the voltage this voltage will be dissipated or this voltage will be dropped inside the MOS because we have applied the voltage V. That is the V. V is applied voltage at the metal, right?
Okay, sir.
Okay, and this part is grounded. Okay, so the applied voltage is across the whole device, right? So how that voltage will drop inside this device is some part of the voltage will drop across the insulator. Okay, because
Yes, sir.
across the metal there won't be any drop. Okay,
Yes, sir. Yes, sir.
because that is, and some part will drop across the semiconductor.
Yes, sir.
So, and whatever the band bending is, that is the dropped voltage because there is no drop in the voltage as the bands are flat in this region.
Yes, sir. Yes, sir. Okay.
Okay. So this is the psi s, which is the dropped voltage across the semiconductor. Vi is the dropped voltage across the insulator, and that is equal to the applied voltage.
Yes, sir.
Okay.
Yes, sir.
Yeah. So, and this Vi is equal to epsilon I into D. So, epsilon I, this is the insulator, this permittivity.
Permittivity, sir.
Okay. And that is equal to the Qs, that is the charge across the insulator, and which is equal to the metal. Okay. Qs into D by epsilon s I. So, this is nothing but a capacitor thing.
Yes, sir. Yes, sir.
Okay. Got this thing?
Yes, sir. Exactly, sir.
Okay, and this same thing is shown as a this is electric field, not the epsilon. Okay, this is the electric field. This is the epsilon I. Okay, this is the electric field. Okay, give me 1 minute. Someone wants to join the meeting. Okay, this is the
Okay, sir.
electric field. This is the electric field. I hope you got these things.
Yes, sir. Yes, sir.
Okay, so anything else in this thing?
No, sir. Up to that, everything clear, sir.
Okay, so now we can see. I need to check into this one but I'll try. I'll try my best in this one. Have you seen the CV characteristics of a mouse before?
Yes, sir.
Okay,
Yes, sir.
okay, okay. Let us see this thing. So, this is an what type of? Okay, in this case,
These are P-type substrates, sir.
this is yes P-type substrate. I can see that this
Yes,
is a
sir.
P-type substrate, and when you apply a negative potential here, so there will be an inversion layer. No, there will be an accumulation layer, right?
Accumulation layer. Yes, sir. Yes, sir.
Okay, so when there will be an okay, let us see. This is a let us see. This is a metal. This is a metal pad. Okay, this is a semiconductor. No, this is an insulator. Okay, metal. This is metal. Okay, metal.
Yes, sir.
This is oxide, or this is an semiconductor. Okay, this is MOS. I am showing in a vertical direction, vertically. Okay,
Okay, sir.
do you understand these things? Okay, when we apply a what P type we have taken up, when we apply a negative voltage here, okay, when we are applying negative voltage, so there will be a positive charge at this point in metal, right?
Yes, sir.
And there will be no, there will be we are applying negative, there will be a negative charge, sorry, there will be a negative charge at this point, and there will be holes that will accumulate at this point, right?
Yes, sir. This is accumulation, sir.
Yeah, this is accumulation, and that thickness of these charges will be very, very thin. Okay, because holes are very abundant. Okay, and in the same case, in metal, electrons and holes are abundance. Okay, so there will be the accumulation will be these will be very thin, very, very thin. Okay, the interface inside the thickness of the charged layer. Can you understand that thing?
Yes, sir. Yes, sir.
Okay, so this will act like a parallel plate capacitor. Okay, because there are there whatever charges are there, whatever potential drop is here is across this only. Got the point?
Yes, sir.
Got the point?
Yes, sir.
So this, so
Yes, sir.
the potential, this is C by Ci. Okay, C, the capacitance is because of the insulator only, because of this oxide layer only. In
This is a CI, na?
C by Ci, C is the total capacitance.
Oh, okay, okay.
Okay, Ci is the insulator capacitance. Okay,
Okay, sir.
so the capacitance will be because of the insulator material. Okay, so if the capacitance is because of the insulator, Ci by Ci is equal to 1. Got this thing? Because C, that the capacitor that we are measuring, okay, this is the capacitor that we are measuring, that C. Okay,
Yes,
this,
sir.
and in over this C by Ci, okay, so we are measuring C by Ci, C by Ci. Okay, C that we have measured, this is the measured value C. Okay, so whatever we are measuring, that will be equal to the insulator capacitance, right?
Yes, sir.
In this case, when we are applying a negative voltage, right? So that is the accumulation region. In accumulation region, that will be a flat. Okay, in accumulation region.
Okay, sir.
In accumulation region. Okay, so when you apply the potential, you start applying a potential, a positive potential, right?
Yes, sir.
You apply a positive potential, that is the VDC. Okay, so whenever you see, this is the how you measure the capacitance. V is equal to this V, applied V is equal to VDC plus a small signal of the sine signal. Okay, this is how you measure the capacitance. Okay,
Okay, sir.
okay. So in this case, this is the V applied voltage. This is the applied voltage uh, VDC. What I am looking for is when you go in a positive direction, what will happen is it will deplete the charges, right?
Yes, sir.
When it will deplete the charges, so let us say I'll just take one new slide. I'll tell you.
So the width of the capacitor will be increased, sir.
No, what I want to tell you is a bit different thing. Okay, so when you this was the this is a metal layer. Okay, this is a oxide layer. Okay, metal oxide, and this is a semiconductor layer. Okay, do you understand this thing, right? So
Yes, sir.
when you apply, this is a p-type semiconductor. When you apply a positive potential here, positive, so it will deplete the charges, right? It will deplete the charges, and there will be a depletion region, right? So this is the depletion
Yes, sir.
region. Okay, when you increase the positive potential, the depletion region will increase, right?
Okay, sir.
So 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 what will happen is this the okay the capacitor, what was coming from here only in the in the accumulation region, the capacitance will come from this as well as with this one.
Yes, sir.
Okay, so this is in series with this, right?
Yes, sir.
So 1 by C is equal to 1 by C. This is the insulator Ci plus 1 by Cs from the semiconductor. So this is how a series capacitors will be added, right?
Yes, sir.
Okay. So as we increase the voltage, a this width will increase, right?
Yes, sir.
So the capacitance will decrease,
Capacitance decrease. Yes,
right?
sir.
So in this one, where were we? I think in this one, we were, right. When we increase the potential, so the capacitance is decreasing, right? That
Yes,
this
sir.
this is C by Ci. So we will solve the equation later maybe. So you can go through the lecture because I don't remember that much of equations now as you just requested. I am telling you. Okay. So
Okay, okay, sir. No issue.
okay. So and one more thing is there are certain graphs, right? Okay. Let us go one by one with these. Okay. So whenever you are measuring a capacitor, okay, whenever you are measuring a capacitor, there is a small signal, right?
Yes, sir.
So as you are applying, so this is, let us say, this is the interface. This is the depletion region. Okay, this is the depletion region. When you apply the potential, when you apply a sine wave with some frequency, okay, with some frequency, so this depletion region will go up and down, right? Because of this is the total potential that is applied across the device, right?
Yes, sir.
Because of the sine wave, there is negative, positive, negative, positive. The total potential is increasing and decreasing, right? So this is what I told you here. So if you increase this potential, whatever we are applying V here, so the width of the depletion region will go up and will increase and decrease, right?
Yes, sir.
So that it will affect this capacitance as well, right?
Yes, sir.
Okay, so there are two things. So if the frequency of the signal, if the frequency of the signal is high, okay, if the
Yes, sir.
if the frequency of the signal is very high, so the thing is here the charge carriers are generated at the interface when we invert this. There is an inversion now. This inversion, when we increase the potential here very much, the inversion comes. This is the inversion region, right? In inversion, what happens there? The holes are not, the electrons are not coming from the semiconductor at the interface, but they are actually generated at this interface. Got the point?
Okay, sir. Okay,
Because,
sir. Okay.
because at this point they are actually generated. Okay.
Sir,
So
but the electrons are generated due to the DC voltage, na?
this is whatever it is. Okay. Actually, let us say we have applied the frequency, just forgot about the frequency. Let us say you are at the DC voltage only. Okay. So you have applied only DC voltage, no AC voltage is there. Okay. You went in the inversion region. Okay. In the inversion region, when you apply the potential, you have applied some potential, very high positive potential you have applied. Okay. So there is an some depletion region and some inversion region here, right?
Yes, sir.
Some depletion. Okay, from here I will show you. There is some depletion region. This is the depletion region. Okay, this is the depletion region till here. Okay, this is the inversion region. Can you see this thing? This is the
Yes,
inversion
sir.
region.
Yes, sir.
So if when you are applying the AC signal over that at this position, okay, so this uh, signal, this can go wide and this thing, right? WD.
Yes, sir. The width can be increasing or decreasing based
It
on the
can be,
frequency.
yeah, based on the frequency. But if the frequency is low, this uh, there is generation can okay, there is generation rate G. You remember this thing?
Yes, sir. Yes, sir.
So if the AC frequency is lesser than the generation rate, okay. If high the frequency, okay, it is very difficult to generate. At it is very difficult to cope up with the generation rate. Okay.
Okay, sir.
Maybe I am confusing you, but yeah, for the lower frequencies, the charges will be generated in this region. Okay, in this region for lower frequency.
Okay, sir. Okay.
Okay, for lower frequencies, so this will be the graph. This will be the graph because for lower frequencies, charge this capacitance will be because of this region only, because electrons are added in this region and removed from this region if the frequency is low. If the frequency is very high, so it cannot generate the charges. Okay, generation rate is uh, is lesser. Generation, there is some time it takes to generate the charge carriers, right? Okay, but
Yes, sir.
but it can knock out a hole from from here at this position away from here. Okay, so the capacitance will be lower. Okay, because of
Okay, sir.
this, because the charges are added at this junction, so D is very high. Okay, C is equal to Q by D. So you remember this thing, epsilon A by epsilon by D,
Yes,
right?
sir.
So at larger the distance, this Q is added or removed. So what will the capacitance will be lower, right?
Sir, actually, when you apply low frequency,
Huh?
The electron will generate.
Yes, electron and holes will generate.
Yes. But sir, when you apply high frequency,
It is very
the
difficult to generate in that less time period of time period. Okay, generation rate is not that high. Okay,
okay. Okay.
okay, that is the
Then sir, then
tau generation rate, that is time period of okay when okay, so this is the thing that will come. Okay, this is the thing that will come.
so this is for high frequency, na sir?
This is for high frequency. So for
Okay,
D,
okay, sir.
I need to go back and need to learn for this one D. I cannot tell you right now because I don't know about this D. But in between the frequency, this happens. This graph happens. For low frequency is this one, high frequency is this one, and in between is this one. So this is the deep depletion region. Okay, D is the deep depletion region.
Okay, sir. Okay.
Okay, so I need to check this thing once. So maybe in the next class I can tell you. Okay.
Okay, sir. Okay.
Uh, this is a bit confusing, but if you go, I'll share my both the lectures. Actually, I'll last time I taught this thing, so I'll share that I in detail I discussed these things. Okay,
Okay, sir. Okay. Okay.
and so these are the formula things. So you need to just go once through these. So I don't remember all these things now. So that you need to see. So this is the thing that has been shown. Okay. So this is because of the DC, and this depletion region is created
sir.
because of the AC. Okay.
Okay. Okay, sir.
That is the thing. And this is the thing that we have discussed already. Actually, very slow, very fast, slow and fast. These things. Okay, if actually this
Okay,
deep
sir.
depletion region goes when both these are fast. Okay, we are
Actually,
changing
sir,
the
whatever sir told that if I move from zero to negative to positive very fast in DC level,
yes,
then the D curve will be formed, sir.
this deep depletion region goes.
Yes,
Okay,
sir. But
in this
AC will be not affected, sir, in case of deep depletion. AC
AC,
might be fast or slow, sir. It cannot
AC
be
can be
affected
fast.
the
AC can be fast or slow. Yes.
deep depletion region is reached only when the you can move the DC voltage very sweep fast.
Yes, yes. We if we sweep the DC voltage fast, then it happens. Okay.
Okay, sir.
So the same thing that I told. Okay. So the DQ because of the AC voltage is added where? At low frequencies, it is added in this region in the inversion layer. Got this point? For the lower frequencies.
Sir, sir, my question is that if I apply low frequency, the first picture DQ level will be ups and downs.
Yes, in this one will be the ups and downs.
Figure A, sir. But sir, if I apply due to AC signal, the width of the DQ level will be changed from below to high for C figure.
I couldn't understand your question.
In C figure, due to apply due to apply AC signal, the width of the depletion region will be changed.
width of the depletion region is changed because it cannot generate the charges so fast because the frequency is so high.
Okay,
So,
okay, okay.
so the depletion region width is changing to to
Okay, so,
to
so sir,
compensate the charges that we have here, because here is the abundance of the charges, right? Because of the metal. This is the metal. Okay, here is the abundance of the charges, and this metal charges, there is no need for the generation or recombination or anything, generation or accumulation, anything. Okay, but in this one,
okay, sir.
this is the semiconductor, this is not a metal, so there is no abundance of the charges. We are doing it with the minority carriers, right? If it would be
Yes,
for
sir.
the majority carriers, there won't be anything if you go with the high frequency or the low frequency, because can you see this region? This region is same for high frequency and low frequencies. This is the same for the, because this is the accumulation region.
Yes, sir. Yes, sir.
Okay, so there is no change in the accumulation region for the high frequencies or low frequencies. Okay,
Okay, sir.
yeah. So anything else?
Sir, in last chapter,
Okay, yes.
just tell me the sir effect of width increment and the uh, length increment difference A and C. What is the difference, sir? A for low frequency and C for high frequency.
Yes. So in this figure you are asking.
Yes, sir. Yes, sir.
Yes, A is for low frequency and C is for high. So this picture is depicting where the charges are added with the with this application of this voltage, where the charges are added or removed, because there is a sign signal, the sign omega day. Positive it will added, the charge will added. For negative it will be removed, right?
Okay, 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 sir. Okay.
Yeah. So it
And
will
sir, for
increase and decrease.
sir, D for sir, uh, deep depletion.
D is for the deep depletion region, because
Okay, okay, sir.
we are already here. We have, this is the maximum WD could go. Okay, but we have swept the DC voltage so fast that it cannot add the charges here, but it is adding the charges here. Okay, the DC voltage. Okay,
Yes, sir. Yes, sir.
and now the AC signal is over that. Okay,
Okay.
yeah, that is the thing. And got the point?
Yes, sir. Sir, kindly understand, if possible, sir, formula for C in case of high frequency and depletion.
So your formula, this thing.
Yes, sir.
Okay. So mhm, do you, okay. Mhm. First, let us go with this one, low frequency one. Okay.
Okay, sir.
So this is, let us suppose there is a parallel plate capacitor. Okay, this is the first one, and this is two, and there is some dielectric in between these two. Okay, so when you apply a voltage here, so there will be some capacitance, right? So just apply an AC signal here along with that, that is we have applied, right?
Yes, sir.
Okay, so when you have applied the AC signal, so the charges will be added and removed at this point, at this junction, right? Then let us say this is metal plate, this is metal plate, but the charges are added and removed at this point, because this is a metal, abundance of the charge carriers, and that will be the at the interface, right?
Okay,
Charges
sir.
will be at the interface, right? So when instead of this metal pad, let us replace it with the semiconductor piece. Okay, that second one, let us replace this with a semiconductor one. So you are already in a deep depletion region. Okay, this is the deep depletion region, the first one. Okay,
Okay, sir.
so you have done the band bending such that you are in this case in the deep depletion region, in inversion region, not the deep depletion, sorry, in the inversion regime. Okay, so you have
Okay, sir.
charges here. So when you apply a small more potential here, okay, this your Fermi level will go up and down at this junction, right? When you apply positive or negative, you increase this voltage, positive. Okay, so this Fermi
Yes,
level
sir.
will go, this EI, the bands will bend more, right?
Yes, sir.
If you decrease this voltage slightly, this Fermi level, this bands will bend less, right?
Upward.
Yeah, upward
Yes,
and
sir.
downward. So this increment and decrement, let us do this increment and decrement with a sine wave, a sine of omega t. We note sine of omega t with some frequency. Okay, so
Okay, sir.
your Fermi level will go up and down with that frequency.
Yes, sir.
Okay, so if your Fermi level is going up and down, so you are increasing and decreasing the charge carriers here, right?
Yes, sir.
Okay, so if you are increasing and decreasing the charge carriers, so that will affect your capacitance, right?
Yes, sir.
So
Yes,
so
sir.
we are increasing and decreasing the charge carriers at the interface. Okay,
Yes, sir.
because if the frequency is less, okay, so we are increasing the and decreasing the charge carriers at the interface. The so here was the interface and here is the interface. So the this uh, capacitance will be from this insulator, right? Ci, right?
Yes,
In
sir.
in this and that is the same case. This thing is what is depicting, right? Okay, we are in the
Yes, sir.
inversion regime and this is equal to the Ci. The capacitance that you will measure is equal to the Ci. Okay, and this is the same thing that is given Cox or Ci, oxide capacitance, Cox. Got
Okay,
this?
sir.
For the lower frequencies. Okay, let us go back in the same figure and now let us go for a high frequency. Okay, now we are increasing and decreasing this voltage with very high frequency. Okay, so this Fermi level cannot cope up with that high frequency. It cannot go up and down that much faster because
Okay, sir.
the generation cannot happen that much faster rate.
Okay, sir.
Okay, so what will happen is, so this the depletion region will expand a bit more because here
Yes,
are
sir.
the charges, because we have applied the potential, so here are the charges, so that same amount of charges should be in this semiconductor also, right?
Yes, sir.
So that same amount of, for the same amount of charges that cannot generate here, but will 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 expand here, will expand this region. So there will be immobile charges here. Got the point?
Yes, sir.
Okay. So and that so what we are getting, the capacitance. So there is no effect in this region, right? Got this point? There is no effect in
Yes,
this
sir.
region, but what is affecting is at the width W. W is the initial width of the depletion region. Okay, I'll just go back. Let me see if there is something is there. I'll just see. No. Okay. Just give me 1 minute. Ha. In this one only. In this figure only. Okay, we have. So initially, can you see this thing? So this was the maximum width was here. This is the maximum width that could be in of the depletion region, and then the inversion happens, right? But
Yes, sir.
if we increase the frequency, so the addition cannot be here, but the addition will be here. Got this point?
Yes, sir. Because due to high frequency,
High
carrier cannot generate it.
Yes, cannot be generated. So so the capacitance will be affected at this position, right? Because of this charge is at this position, right?
Yes, sir.
So so this D uh, was D is the width, or no, not the width, the thickness of the oxide layer. D is the thickness of the oxide layer. Okay.
Yes, sir.
So, or we can say T ox, oxide layer thickness. D is equal to the T ox. Okay. So, the capacitance will be 1 by C is equal to 1 by C oxide, right? Plus 1 by semiconductor, C semiconductor. Got the point?
Yes, sir.
Because of this thing. And the oxide capacitance is constant. That is, nothing is happening to the oxide capacitance, right?
Yes, sir.
Okay, that is the constant. But what is happening in the so
Depletion capacitance.
in
Means
in this one,
semiconductor capacitance.
so that will be equal to the W this thing. How much is the XD max? XD is the width of this region, depletion region. Okay, so do you understand this thing? C is equal to epsilon by D,
A by D. If epsilon A by D.
right? Epsilon by D,
Yes,
right?
yes, sir.
So that is the same thing. Both this is the oxide capacitor and this is the semiconductor capacitance. XD max, epsilon S is the permittivity of the semiconductor material, and epsilon OX is the permittivity of the oxide material. Got this thing?
Yes, sir.
Because this is the capacitance, because charges are added at this point, so the capacitance will the D term will be because of this thing, right? Got this point?
The last sentence, D term is what?
Okay, XD or D is the Tox only, nothing.
Yeah, yeah, yeah.
Tox is the D is the thickness of the oxide layer.
Yes, yes, sir. Yes, sir.
Okay, and XD max is the width of your
Semiconductor capacitance.
depletion region.
Semiconductor capacitance.
Depletion region. Okay,
Yes, sir. Yes, yes, sir.
this is the thing. Got the point?
Yes, sir.
Yeah. So, any other doubt?
No, sir. Up to that, it is clear, sir.
Okay, and no other doubt. So these are the equations that you need to go through. Actually, I don't remember these equations. I just go with all these things. So how these things are happening, I just go with that. So I don't go for the equations. Never I have actually remember these equations. I never grabbed all these things. So you can just understand the concept and go with the concept. You can solve all the problems.
Okay, sir. Okay.
Okay. So a strong inversion. I don't remember any of these equations, but I know how these things happens. Okay.
Sir, if possible, sir, in next class, sir, you can discuss this topic.
All these things. Yeah, sure. I need to
No,
go.
no, no.
Yes.
Only the equation part, sir. You can understand that. You can already discuss the concept, sir.
Yes, I have
Now the
already.
equation part.
Okay, equation part I will discuss in the next class. Okay. Yeah, I'll try to do that.
Okay.
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 So, well, okay, let me see. Someone is there. Okay. Uh, if is there any doubt apart from these? Hmm? Somnath and
Sir,
Sandeep. Mhm.
my side, sir, I must try to solve the equation and assignment, sir.
Okay, no problem. Yeah,
If I face some problems, sir, I can discuss with you, sir. Okay.
yeah, sure. Next Tuesday we will meet again. Okay.
Okay. Sir, in this week, you can take 2 classes, na?
No, I take only one class on Tuesday from 6 to 8 p.m. So
Okay, okay.
whatever you have doubts, I will try to solve them. Okay. So if you can tell me prior to that next class, I can prepare for that as well.
Okay, okay. Sir, please provide your mail ID, sir.
Yeah. Okay. Should I write down in the comment box?
I can, yes, sir, you can write down or I can write in, if I you can
Okay.
write down, sir, in comment box, sir.
Okay. Okay. Just give me a minute. Okay. Just see. You can just drop me a mail before any class so that I can prepare for that as well.
Okay, sir.
Yeah. So can we close this today's session? Or
Okay, sir. Okay.
okay. Okay,
Sir,
that's all for
your mail
thank you.
ID will be,
Huh?
your mail ID will be not showing, sir.
I just texted in the in this comment box. Can you just check once?
Sir, after you can, okay, I can check it, sir.
Just see, just see. I have pinned that.
Okay.
Okay, just see. Check this one. Got this?
Yes, sir. Yes, sir. Yes, sir.
Okay. So after leaving this session, just note it down because after leaving this session, you won't be able to see that mail ID.
Yes, sir. Yes, sir. That's why I'm telling, sir.
Okay.
Okay, sir.
Noted.
Okay. Thank you, sir.
Okay.
I can add down. Okay.
Okay.
Thank you, sir.
Thank you for joining this session. Thanks a lot.